I'd like to welcome all of you out there in Radioland to the next installment of our ReproNim monthly webinars. Today, we'll hear from Dorota and the team working on the TestKraken software for testing scientific workflows. This is being recorded. The recording and the slides will be made available and tweeted out and on our standard release pages for that. And before I turn things over to Dorota, just a reminder that next month's webinar will be February 7th at 2 p.m. Eastern Standard Time. And we'll hear from our Interlex and PineIDM and Terminology Services team with some catchy title to be determined. And again, stay tuned to your information channels for that detailed announcement. So without further ado, let's hear about testing scientific workflows with TestKraken.
Okay, thanks. So my name is Dorota, for those who don't know me, and I work with Satra at MIT. So this is webinar, but we have some people live. So I mean, it's kind of weird to record webinar, but you still can interrupt me. So obviously I cannot see you, but if you have any question, you can interrupt me. Okay, so I will start from short motivation and talk about my general idea about scientific workflows. I will be talking later about testing and reproducibility, and then I will make some introduction to TestKraken and niflows at the very end. Okay, so first, scientific workflows. So this is like maybe like very simplistic view of how I see like scientific workflows. So in the past, it was like slightly different than it is now. It is now. So the experiment design were not necessarily simple, but the measurement tools were like probably like much more like less complex, and often were like designed by scientists. It was later like the measurements were like also like added to some like fitted to some physical law, and it was like some set of equations were created by scientists. And then it was like scientific group were making some computation. It was usually like single scientist or like group or small group of scientists that were often also the same people as the one that designed the experiment. Slightly more realistic. And at the end, it was at the end they had a result that they shared with scientific community. And it was usually like some short article or presentation. And it was like from the very beginning, like already in 17th centuries, people started like talking about the importance of reproducibility. So basically it was like, it's not a new idea that the experiment that you cannot repeat should not be significant for science and for scientific community. So now that the time has changed and things look like slightly different. So first of all, like I would argue that the measurement tools like became like highly complex. They were designed by big teams that were often like usually not the same people as scientists. The theory also like became more complex, mostly because we often ask like more complex questions, and also because we are using more complicated tools to measure things. And yeah, and we have like more complicated equations, and we have like more data. So we often need help from computers. And we work usually in much bigger group of scientists and software developers. And often like not all people are involved in science as much as it used to be. Some people like just like software developers. But yet like still like the way how we present results, it's often the same. So it's like still publication, and yeah, and it's actually like just much more like publication, like publish every year nowadays. So that is not like, that's often like people are saying that the current results are extremely hard or even impossible to reproduce based on other articles. And not only other scientists don't know how to repeat the experiment, but even the scientists who publish the work and who committed the experiment are not able to say how to repeat the same experiment in future. So it's true that it probably became like just harder to assure that research is reproducible, but perhaps also because we have like so many new tools, so many much more complex computer programs, it is even like more important to actually be able to reproduce the results and know the limitation of the results. So here we mostly focus on computational part. So I don't care for now like the experimental design, the measurements tool people are using. But we start from the place that we have data sets and we're using some software to analyze the data. So in an ideal world, we have enough data, we have enough good resolution and well-defined variables, and everyone is measuring the same. It's also like ideally we know exact analytical solution, and we have enough computational power to actually employ this analytical solution to get to the results. However, like in the real world, it's often like not the case. So we often do not have enough data. We hope that it's at least representative group, but we do know that it's not always so easy. Could be collected in various places using like different tools, different scanners. Hopefully we at least have information to at least, and we are at least aware of some differences, but this is also not always the case. And we often also like don't know exact solutions. So we do not have like analytical equations that we can use, but we actually use like more complex algorithms. And often like we use like many simplification and many, we are assuming many different things that it's not always obvious that this is the perfect, the best assumption we're using. And other scientists might be using slightly different assumption that it may be important or may not be important, and it's not always easy to say. So so let's imagine like we have like situation that we have two different data sets that are like analyzed using different software in different computational environment and giving different results. So and now we are like, sorry, like it's like and now I would try to make connection between like reproducibility and testing. So when we have this like multiple results, it can be, we would like this result to be like pretty close if we're expecting that it should give the same results. And then if we're like, the results are close enough, we can talk about the answer to our question, or this answer to a question that we ask. However, sometimes the results are like all over the places. And it's hard to tell that we have like any answer to a question we are asking, because we are clearly do not understand something. We either like making some mistakes preparing this experiment, or we are not including the important factors that we should be including in our analysis. So there are like many examples also in like neuroscientific community that shows that like different groups are making different like data analysis that in theory should be similar, but we're like giving very different results. And this is only just one of the example. So we talk a lot about reproducibility. And I sometimes use like reproducibility, sometimes re-execution. And here, like, I just want to like define what do I mean by reproducibility and re-execution. So basically, we use often the term reproducibility as a kind of spectrum of different things. So basically, we can imagine that in the cases that I described before, we can imagine that we have like slightly different data sets, and we can have like slightly different analysis and computational environment. So if we are saying that the data sets are similar and the computational like analysis are similar, we're expecting that the data should be also, the results should be also similar. But and in the situation when we are checking different, so the simplest situation is when we are trying just to repeat exactly the same analysis using exactly the same data set. So in this case, we are using like the term re-execution because we're basically trying to repeat exactly the same things, and we hopefully really get exactly the same results. However, we can also like ask question, what if we use the same data sets, but we're using slightly different analysis or slightly different computational environment? It is still like similar enough that we do not expect any other big differences, but it is something that has to be always checked. And this is what we call like robustness, checking if our like result does not depend too much when we are changing slightly the analysis and computational environment. The second situation might be that we are not changing the analysis and computational environment, but we're changing slightly the data. So this is something what we call like replicability, basically checking if for similar data, our analysis can still give similar results. And of course, we can also like have like both, like change slightly the data set and slightly the environment, and that would be like checking if the results are, you can generalize the results. So for TestKraken, so basically TestKraken is one of the tools that you can that is designed to help you to check if your analysis is and the results are reproducible. So so basically the main goal of TestKraken is testing workflow in various environments. In terms of tools that we're using NeuroDocker to create Docker files, Docker to create computational containers, Python to build and run a workflow with the analysis, and CircoCI for continuous integration. And I will be talking about this later. So coming back to this figure, so basically, especially like right now, TestKraken is mostly concentrating on the robustness test. So basically, we're using the same data sets, but we are changing the computational environment. So we are checking if our results are robust. Oh, okay, sorry. That was like, I forgot to change the slide, I'm sorry. So basically, so in order to prepare the workflow to be used by TestKraken, is that we have to you have to specify the TestKraken spec YAML file. You have to provide data and you have to provide scripts. So the most important thing is to create specification. So basically, in the specification, you are providing information about computational environments. You are providing the data and scripts locations, the analysis specification, and the test specification. So for the for the environment specification, we are using a similar structure as NeuroDocker, because basically we're using NeuroDocker to create the Docker file. For those who don't know NeuroDocker, I will provide the link at the very end of my slides, but this is a Python package that helps you to create Docker files. And basically, like, it covers all popular software that is used by neuroimaging. So basically, like, it uses, we always have to specify the basic image. And we can also like specify other like software that we're using, including, for example, like Python version dependencies, FSL, AVNI, and many more. So you can check for newer Docker specification what can be included in the container. And basically, like, we are trying to make flexible how to create environments based on the specification. And for this, we're using two entries, env and fixenv. So for env, the idea is to create all combination of environments specification. So basically, in this example, you have two base images and two versions of Miniconda. So in this, because we are creating all combination, like TestKraken will create 4 different images. 2 for Ubuntu with different version of Pythons, and 2 for Debian with also like 2 different versions of Python. And in fixed environment, you can provide a list or a single environment that is kind of has like fixed environment. So you also have to provide the same keys as in N, but this is like, it is fixed. There's no combination to create from fixed environment. So in this situation, if you would provide both, you would be creating like 5 different environments. The second part was the data and scripts location. So we do have some default location for data, but you can always change this. And it can be either in your workflow path, but it can be also like in different places on your computer. And the idea is also to provide support for data that are not on your local computer, but are like in external repositories. And this is a work in progress, and I will be working on this like soon. And the idea is also like to provide support for DataLab, and that is other like tools that is developed under ReproNim. And similar versus scripts, you have a default location, but you can change this location to different path. And this is a place where TestKraken expects to find the analysis you want to test, and also like the testing scripts that you will be using. So the analysis specification is next. So basically, analysis is what I call is the scientific workflow that you will be testing. So you have to provide commands, and it might require scripts and input. So basically, we are like every single workflow that you wanna test, it has to be either executable, or it has to be script that can be run from command line. So in simple example, it can be just Python and Python scripts that also like provides command line interface. And in most cases, of course, you also you will include inputs. And for inputs, you should provide type, optional flag, and value. And also you might include additional metadata that can be used by Pydra that is used as a data flow work engine, but I will not cover this now. And this is the test specification. So basically, this is the second part of our TestKraken workflow. So first, the TestKraken runs analysis in different environments. And now is the part where we describe the part that is actually testing the output of the analysis. So it contains all information about the analysis output that we'll be testing. And also like includes information about the scripts which should be used to test the output. So we are planning to create basically library of different testing functions that we like for general purpose, but also you can specify in your own testing function and include in the scripts directory. So in this example, like I'm saying that I will be testing two output files, list sorted and average list JSON, and I will be either using test object equal or my test object equal. So in this example, the test object equal is in the testing function directory of TestKraken, but the my test object equal is not, but it is like designed by the scientist and is also included in the scripts directory. So I will show the example based on simple workflow. This is like this is based on the publication published a couple years ago by ReproNim team, and you can find on GitHub and the source code and how to get the data. And here I will show how I use TestKraken to basically to rerun and check the simple workflow in different environment. So basically, this is that was like comparison that was presented in simple workflow results, and as you can see, for different environments, some of the results were like significantly different. Okay, so this is how is the example of our specification file. So basically, you can see that at the very beginning, I'm asking for two different base image, either Ubuntu or CentOS. I'm asking for two different FSL versions, and I'm using a specific Miniconda environment. And I also like asking for one fixed environment that basically using Python 2.7. For the analysis part is I'm basically using the run demo workflow that is provided by the authors of the publications. And this is like Python code. So the command will be Python. And I have to provide two inputs that are required. So basically I need key to get the data. And I'm asking for three subjects that will be checked in this specific example. And for testing, because I asked for three subjects, I'm basically taking three different files produced by analysis, and I will be checking this with the check output file. So this is how it looks like, the specification, this example. And just to give you an idea how it should, the workflow should be created. So this is not the full code because it would be like too long, but just to give you an idea. First of all, it's very similar. I didn't actually almost change anything comparing to what was done for the publication. Basically, the only thing, so here like there is a function to download file, there's a function to slightly convert the data. And here we are authors were using niflow workflow to create workflow and run the analysis. So this is like standard niflow workflow for people who know the niflow. And the last part was the creating command, like using argparse library to create command line interface. So in this situation, as I mentioned before, I had to provide key, and I had to provide the number of subjects that I want to run. And in addition, TestKraken will provide output dir and working dir. So here basically it's how the code should be prepared to be run with TestKraken, because we have to access this from the command line. And the next is the test script. So as I mentioned before, like we run the analysis and taking the output to run tests. So here is as well, like this is not a full script. And basically it was like more or less the same script authors were using to for the publication. But basically here, like I'm checking the differences between different between the expected value, and that by expected value in this situation, I mean the results that were obtained in this case, like using my local computer. So I'm checking the differences between results of the output and the expected output. And I'm also like just checking if there's any element that is big, like the difference is bigger than like 5%. And that's how I'm like saying that if the test is passing or failing. Obviously, this is up to scientists to choose what doesn't mean that the test is passing or failing. And that's why we are also like providing information about the error itself. And this is also has to have like command line interface. So every single test that you are creating your own, it has to also use ArcParse or other tool to provide the interface. And this is the results. So here you can see, so this is like kind of like screenshot from the dashboard. So basically, this is also like work in progress. We will be extending the dashboard, but here we can see various representation of the results. So basically, like we keep the information about different environments and different version of the software it's being used. So you can see that I'm using FSL, two versions of FSL, version 0 and version 1. I cannot use the mouse one. Oh, okay. So you are using like, remember we have like two different versions of FSL. So version 1, 0 and version 1. We also have different subjects that we are testing. And we have results of our tests. So basically, you have either like a relative error for the specific keys, and you also have just like pass and failed value. And you have also like description of the different version of base image and FSL, and the description of the mini content. So this is basically like introduction to TestKraken itself. Anyone has any questions that you want to ask now? If not, I will like go again to the slide mode to say a couple words about niflows. So this is another project that that is under development. So there's like two things that are related to each other: niflow-manager and niflows. So the basic idea of niflows is to provide a structure that helps you to make your neuroimaging workflows to be fair. So basically to be easy to find, access, interpret, and reuse. niflow-manager provides the NFM command line tools to support niflow creation, testing, and packaging. So basically, the command that we are now provided is nfm init, that basically creates a workflow directory using the templates for like specific language. nfm installs, so it installs niflows from online registry or from local place. nfm build, this is using this is creating the containers that has the package installed inside, and nfm test. So this is place where also we are like writing this part based on TestKraken. So basically, this we create various environments and test the work niflow within the containers using TestKraken. So this is like the only slide I have from niflow-manager, but just to show you that this is actually like using similar specification as TestKraken. So requirements is used for NFM build, and this is basically the requirements, the basic requirements that I needed to insert the niflow. And in addition to this, there is a test part. So for NFM test, basically entire test specification will be provided to TestKraken, and based on this, TestKraken will create various environments and also like around the analysis and test. This is like pretty short because this is just a template. So so basically that's it. What I prepared. So I mentioned like various softwares today. So this is done based on TestKraken is using NeuroDocker, and you can check under the ReproNim repository. There's also TestKraken. I mentioned PyJar that is used within TestKraken to run the analysis and tests, and niflow-manager that is developed. So this is work done by several people from NiPipe and the ReproNim community. And yeah, so
Okay.
I want to thank you and ask for questions.
Thank you, Dorota. Again, it's always a little tricky on the webinar, but if there's any intrepid listeners out there who would like to ask a question, you are free to unmute yourself and introduce yourself and have at it. So I guess I'll take a starting question real quickly. I don't know if you mentioned it, but so in that 3 different tests you did with the simple workflow and different FSL environments and things like that, did they all pass? Did they all fail? Did they?
So in this situation, it was so first of all, because as a reference data, I was using my local results, so it was from OS X environment.
Mm-hmm.
The containers were based on Ubuntu and CentOS, and yeah, there were like differences between the results. The results that I was saved from my local computer and the output produced by the TestKraken, by the analysis using TestKraken framework. And so in terms of like pass and fail, I always like saying that this is kind of a part always that it's up to scientists to define what does it mean the test is passing or failing, yeah, because
Right.
we in different situations we are expecting different differences between outputs, yeah. So it's like we're saying here, like it's up to us to define, is it like close enough to say that we actually know the answer to our question, or actually the results are so different that we cannot say that we have the results and we can reproduce our results.
Right. And in that specific example, one could ask about similarity of the binary images in terms of bit by bit decisions of is it caudate or not, or it could be the summary volume, is the volume of the caudate within 5% or various things. So there's different
so
metrics there.
So exactly. So in this specific example, like the test itself, as I said, like this is not full test. I was like just removing, just keeping some parts only. So here, like I'm basically checking for various keys, the differences, as you said, for different parts of the brain. But here, like my simple like pass fail test is just saying if anything in the list for any of the keys the difference is bigger than 5%, then I'm saying that it's failing. Yeah.
Right.
So, but obviously this is like arbitrary, and that's why basically like we can create as a library of tests, but on the other hand, it's often like, you know, scientists has to think what does it mean that the tests are still passing. Do we expect, and also like it might depends what we are changing, because like here is like simple changes in the convolutional environment and the FSL version. But if we expect, if for example, if we change the not only the FSL version but some parameters, then maybe the changes might be bigger, because we do not expect to be exactly the same with different parameters.
Right. Okay. Another chance for intrepid outsiders to ask a question.
I'll ask a question.
Excellent.
Yeah.
Hi, James.
Hi.
Sometimes.
I was curious for the test scripts, if or like what are the requirements on the output? Does it have to be like a JSON file? Does the JSON file have to have certain keys? Or is that pretty much all defined by us and what we want the test script to
Yeah,
output?
so the idea is that exactly like that it can be, you know, I have a couple examples of testing functions, and I have for various formats, like not this one, because this was specifically for simple workflow. So basically that was already provided by the authors. But yeah, I do have like a couple testing functions that works for different formats, but the library is not big for now. But yeah, in the future, like, yes, depending on your output, so the test should take whatever it's your output. For now, the assumption is that you are providing the reference data. So basically the same name of the file should be in the expected data directory and as the output you want to test. And so the only requirement for now, at least, and I think this is what we will keep it, is that like we still want to like, so all of my tests are written in Python. This is not true about analysis. Analysis can be in anything, but for now tests are written in Python and has to have this this command line interface, and has to take, you know, output reference name. So it has to be like in a structure, in a similar structure as this test, but it doesn't have to be the same file format. This is up to you to decide.
Okay, all right. Thank you.
Okay, any more questions out there? If not, I'd like to thank once again Dorota and the TestKraken team for their work on this and their presentation of it. And just in parting, just one more reminder that next month, February 7th, 2 o'clock Eastern, will be Interlex PyNIDM and some terminology service discussion to be defined more precisely as we get closer. So again, thanks to you all for joining us, and keep reproducing. Doing reproducible science.
Thank you.
Thanks.
Thank you.